Okay, yeah, this is what we were doing last time, right? I believe we finished all these. We did adding to the front, set the node we want to add to the fronts next to what head reference is, and then have head reference what node reference is. Now that's the new front. Adding to the middle, somehow we find the node we want to get it to come immediately after. And with this particular example, we saw we had to be a little careful with the ordering on how we did things, as to not lose reference to the remainder of the list. What I mean is, if we just said current, set your next to node, we'd be in trouble because everything that was after current would be gone, and that would be a problem. We'd lose reference to it, so we couldn't get to it anymore. So we had to say, okay, node, your next is current's next, and then current, your next is node. So node's next is current's next, and then current's next is equal to what node equals. Removing from the front was the easiest. Just say head, you're equal to head's next. That's it. And then remove from the middle. It's not too bad, but it's kind of the same idea, except it's previous. Your next is equal to previous's next. Here I'm doing it with 2 reference variables. You really don't need the 2. You can do it with 1. Right? I don't need a reference to current here, right? If I had previous, so with 2, I could say, okay, previous, your next is current's next. And that would eliminate current. But I don't even really need that. I could just say previous, your next is previous, next. Right? All right, cool. Any questions about any of that adding and removing? And adding and removing from like the middle is the same as the end. The algorithm would be identical. It was the beginning that was the funny case. All right, so a node implementation. So remember, I know I might sound like a broken record, but it's important that I keep saying it. When I have a node variable, I don't really have a node variable. I have a reference to a node, right? They're always reference variables. So we got to be very mindful of when I say node, like some var equals something versus some var dot something. And I'll emphasize this as we go. So if a reference variable contains a reference to an object, a link structure uses these references to link the structure together. The node implementation for a singly linked structure is kept very simple. You will notice there is not going to be a class for a linked structure. There is no class for a linked structure. All we have is a class for a node. But then when we string these nodes together, we get the linked structure. Now we can use these linked structures to make a stack, for example, which is what we're going to do. So for our node implementation, it's going to be kept ridiculously simple. It's going to be a ridiculously simple object. We're going to have a field to keep track of the data. It's going to be a reference variable to some type t, because our node's going to be generic. So it's going to be a reference variable to some data of type t. We need to keep track of the successor, which could be null, right? It could reference null if there's nothing that comes after the specific node. But a field to keep track of the next node, a node of type t. And constructors and getters and setters. Now we haven't talked about setters yet. Now we're going to make a node implementation that is mutable. We can change the contents of the node. We could do this with an immutable version pretty easily. In fact, arguably, that's maybe a good idea. I don't know. It might even make any implementation we do even easier because we don't need to think about mutability. But for whatever reason here, we're going to make it mutable. That's all to say we have our getters, but we also have a setter for each of the 2 fields. A getter, an accessor, is get some information. A setter is to mutate, a mutator. So getters are called accessors. Setters are often called mutators because they mutate the contents. So I have a get data that just returns the data. But then I also have a set data that changes what data references. But that's the whole class right there. That's it. Really simple. I'm not going to bother with an equals. I'm not going to bother with a toString, because it's just a very simple little class. There's nothing particularly powerful about this class in and of itself. It's when we use them together that it gets interesting. But that's the whole class right there. So any questions about this right here? This node class. All right, it has the two fields, data, next. It's got two constructors, one, this like default one, and then another one that takes some specific data that we can give the node upon creation, and then set its next to null. And notice that the default one it uses that constructor chaining thing again, where it just passes the data as null. That's all. Get, return data, set the data, and so on. Any questions at all? All right, so, you know what, I'm going to copy this. I'm going to go down here, new class. There. I've got my singly linked node class here, and I'm going to go to just lectures, and this is going to be where I just play a little bit around with it. So this is just exploring the implementation. So we'll do it one piece at a time. If I run this, what is this code doing? Well, it's creating a reference variable to a node that's going to hold integers. And the reason we know it's integers is why I specified it in like the triangle brackets. The node reference variable is called head, and it creates a new node, and I used the second constructor there where I specified the data I wanted to be in there. I want it to be 0, because. So then when I say system.out.println head.getData, I see 0. That's what got printed out there. That's all. Nothing here should surprise you. Here. So now, creating two new reference variables. I'm going to leave head alone. Sorry, let me be clear. I'm going to leave the reference variable head alone. What head references, that's going to be used a bunch. But the reference variable head is being left alone. I want to have this reference variable exist, and I want this reference variable to exist such that it's always referencing the beginning. I don't want to lose reference to the beginning by accident, because if I do, what's going to happen? Who can tell me? I'll lose reference to the first thing, which means I lose reference to the next thing, and the next thing, and everything linked along. Exactly. So I create thing, I got a current node that's going to start by referencing what head references, so I have an alias for head, and another thing called new node. And then for int I, starting at 1, and well, it's less than 10, I++, the new node is a new node with the value I in it. The reason I'm starting at 1 is, well, I already have a node with 0, so whatever. So I create a node with the value 1 in it. And then I say current node, your next is the new node. I set its next to the new node. Right? So if I draw that, hopefully this works. Nope. Not too bad. All right. So here's what I have. I've got my initial node. I'm going to draw it as a block with the number 0. At the back, can you see that decently well? Good. Now I have head. I'm just going to refer to it with an H. Okay? I also start with, what is it? Current node, I'm going to call it C. Starts referencing that. Then I've got new node that just exists, whatever. So the first thing, new node may equals a new node. So I'm going to have like new node. I'll just call it N here. It's going to create a new node. Put the value 1 in it. That's what we have on line 15. Then I'm saying, okay, current node, set next to new node. Pay very careful attention here to when I'm using equals and a setter. Very important to understand and notice the difference here. So on line 16, I say current node, your next is new node. So current node, your next is set to what the new node is. That's what happens, right? Any questions? If you have a question, now's the time to ask. Yes?
How come when you initiate the node, you have like integer with a capital I instead of int?
Because, good call, good catch. Whenever making something that's generic, you can't have generics of primitive types. But what you do instead is you just use, so then you go like, but I really want an integer in there. And you go, yeah, that's great. You just use the object version of the primitive type. And there is, integer is int. There's also an uppercase D double. It's the double version, and so on. And there's a lot of reason for it, but one really important reason is the object version must inherit from the object class. And remember, from the object class, we get some of those methods for free that are guaranteed to exist. Your equals, your toString, and so on and so on and so on. Whether you implement them your own way is irrelevant. But those methods exist. So when it's an object, there's some consistency that we know about the information in it by default. When it's a primitive type, you don't really get that type of stuff. But good catch nonetheless, right? Who else noticed that? Who else is like, okay, well, yeah, I noticed it now. And everyone else is asleep. Okay, well, good catch nonetheless. All right, back to where we were. We created the new node, and then current node.set next new node. So I used set next. I said current node set next to new node. But the next line says current node equals current node get next. So what's happening here? We say, I'm going to grab an eraser over here first. I ask, current node, what's your next node? Oh, well, that's this. We just said it. Current node's next is an alias for new node. I could write the exact same thing here. I could replace the right-hand side of that expression with new node. Because current node's get next is new node. Because, well, I mean, the previous line just did that. But I use current node.get next here. So I say current node get next, that's this. And then I'm saying current node, you reference that. So I'm not modifying anything about this node. I'm modifying the reference variable. Not the object, the reference variable. The reference variable doesn't reference this anymore. It references. Marker didn't just die. That one. Okay? We go back to the top of the loop. Oh, well, new node, you equal a new node with the number 2 in it. See if I can find a marker that works a little better. Pardon?
Laptop's falling asleep.
Oh, thank God. It's always the worst when I have to enter a password again. Let's try the red one. If the red works, good. If not, no. Oh, look at that. Now, the change to red has no meaning other than I ran out of blue marker. All right, so current node, set your next to new node. Well, what's current node? Well, it's this. Set its next to the new node. Great. And now current node, get your next. Well, that's this right here. And you now reference this. All right. So there. And so on, and so on, and so on. So it's this iterative process of new node, update the currents next, update what current references. New node, set it next, right? Kind of ba-dump down the line. Any questions about that? Hopefully the drawing helped a little bit, but how it was getting built. Notice though, and I know this is a theme I say a lot in 161, and I'm going to say it a lot in this semester too. There's no trick here. There's no magic going on here. All I did was, what did those 4 lines of code say? That's all we did. We followed the code. When in doubt, what does the code say? There's no magic, there's no silver bullet, there's no magic trick you just haven't learned yet. It is, what does the code say? A lot of time people look for that like, well, how was I supposed to know? Because it literally says it right there. Don't go, it's not more complex than that. If it was, I wouldn't be able to do it. Computer science, each thing we do is a simple little instruction. And if you wrote a line of code that has like 10 instructions in it, don't write that line of code. Write 10 lines of code, each with one instruction in it, because you're making it too complicated. Yeah, you had a question.
So then each node can have its own unique kind of number that'll be its index?
But it doesn't have an index, really. I mean, it does if you kind of be like, well, this is 0. But the fact that this has a 0, a 1, and a 2 in it is just a consequence of me putting integers in there. Maybe I should have put strings.
So you could do A, B, C.
Exactly, I could have. Maybe I should, because then it doesn't confuse the integers with the indices.
So if you change I to like, character A in A, B, C, D.
Yeah.
Then it would assign each node its own unique letter.
Exactly.
Oh, okay.
Yeah, good catch, actually. That's making me think I should change this. The fact that this has a 0 in it isn't because it's index 0. It's just, it's at the beginning and I happen to put the number 0 in it. Maybe I should have put like 10 in there, I don't know.
Maybe you can't be on instead of up.
Or maybe I should have done that, yeah. But there's no index. I can't ask this thing, what's that index, whatever, because there's no indices here. Indices are for arrays.
You could just see what the current is and then.
Exactly. If I wanted that second thing, I have to go like head, next. That's how I get it. I can't say head at index. That's not a.
So then if you wanted the third or fourth, you have to do head and then next.
Yeah. Head dot next dot next dot next. Or head equals head dot get next. Head equals head dot get next. So you can string all these next together, or you could just keep moving the reference variable down as you go. We'll see plenty of examples of this. So, okay, there, and then here, we're gonna print it out. Well, here's how we move down. This is gonna print out all of the contents. Let's run it. Zero, well, we see 0 twice because there's this print. And then I start at the beginning. So I say current node, go back to head. All right? Current node goes back to head. Just ignore this for now. That goes on, right? So I say current node, you reference head. All right? Current node, get the data and print it out. 0. Next line. Current node equals current node dot get next. Okay, current node, what's your next? Oh, that's this right here. Great. Current node, you reference that now. Print it out. Current node equals current node dot get next. Print it out. And so on and so on and so on and so on. I could do this notice that this is not a for loop. This is going to run while current node is not null. Eventually, imagine it was null here. 2's next is null. There's nothing there. Current node equals current node dot get next. Okay, so that will then reference null. it's null. We go back to the top of that loop. Is current node not null? Nope. It is null. So we stop. We're done. There we go. When I say current node equals, I'm modifying what the reference variable is referencing. This isn't new. But the reason I'm emphasizing it is because often when people start learning about these link structures and then they see set next, sometimes people will say like, okay, current.setNext equals current.getNext. It's like, well, no. What that did is it gets currents, pretend currents back here. It gets currents next and then sets its next to next. That wouldn't do anything. That wouldn't modify anything. Set next and get next and set data and get data are about the nodes. When I see dot, current node dot, that's calling a method on that instance. When I say current node equals, that has nothing to do with the instance anymore. It has to do with what is the reference variable referencing. Just to really re-emphasize it, because every year some people get mixed up by this a bit. Any questions at all? All right. Now, I mean, we're not going to do it here, but as an exercise for fun, and this is also going to be next lab. So for those of you on Monday, no, not that lab, but next Thursday, your lab will be playing with link structures, and you're going to be adding to the middle, beginning, you know, you're going to do all those things. But yeah, so, and then here's the warning I just said. Head is not a node. Head is a reference to a node. Head equals some node and head dot set next to some node have two very different meanings. The first means the node reference variable will be updated to reference some node. While the second means that the node referenced by heads next gets updated. So the node referenced by heads field next is what gets modified. Or I guess it's next field that gets modified, not the node that the next field references get modified. Just be very cognizant of this. This is, chances are half of you are going to have a bug about this. I know you're listening right now, you're probably nodding and smiling along. The point of this is, you're going to get a bug when dealing with these reference variables and these nodes. The point right now is that when you hit that bug, I want you to think back to now and be like, oh, maybe, was it that thing? That's the point of this. It's not that you're magically going to remember and never make this mistake. It's that when you do make the mistake, I want you to think of what I was just saying right now, to try to switch. Wait, is it the reference variable or is it the instance itself I want to update? Cool? Variations. So, raise your hand if you thought, why don't you have a reference variable to the predecessor? One person. One person has a head on their shoulders. Where's everybody? Come on. It's a natural question. It begs the question. You know, each node has a reference to its successor. Why not have a predecessor? There's no reason not to. Because right now, if I asked you, like imagine for a moment, I'm at the blue one, and I say, how do you get the predecessor? What's your answer? It's not a trick question. There's an easy way to do it. It's just a pain in the ass. Pardon?
Am I guessing go back to head, go through until you find one where the next node?
Exactly. Exactly what he said. You want to go, well, blue, what's your predecessor? But you can't. It doesn't know what its predecessor is. It only knows what its successor is. So what you got to do is you go back to the beginning and you loop down until you find a node whose next is blue. That's how you do it. Not a big deal. But imagine I had a link structure of 1 billion elements, and I happen to be at the last element. I got to go back to the beginning. How many things do I have to loop over? Like 1 billion, give or take. But if I had a linked implementation, where each node actually had a reference to a predecessor as well, well, suddenly that's a constant time thing, just the node dot previous. Right? Yeah, entirely possible. There's nothing wrong with that. In fact, maybe that's a much better idea. The one we're doing, we're going to keep it simple where it only has one. But you could totally do it with a predecessor. The only downside of this is there's a lot more bookkeeping. Every time you want to remove something, well, you got to make sure you're updating everybody's next and previous. Every time you want to add something, same thing, right? It's not a lot of work, but there's a little bit more bookkeeping. It's really the only downside. Cool. And yeah, you can download the code, play with it. There's the node class, there's a test class for the node class, which is remarkably simple because it's such a simple class. And there's the code I gave you to just kind of play around with it. Any questions about these link structures? Yes.
When you set next, and then it's like some node or new node, is it creating that new node, or is it already created and you're just tacking it on?
Here, can
So, on line 13,
Yeah.
current node dot set next new node, is that new node being created in that line, or is it already exists?
so the reference variable new node already exists.
Oh, it's created right there. I see.
It is. Now, there is nothing stopping me from doing this. And we don't even need this anymore,
Oh, I see.
right? This is entirely fine. It'll work. It should work just as it did. Yeah. So now, when I'm setting it next, I'm immediately creating a new node there and then immediately setting it to next. This is fine. I don't like it this way. Who can tell me why I don't like it this way? Raise your hand if you've got an idea why I don't like this. Really high. I want to see who can read my mind. 1, 2, 3, 4, 5, 6, 7, 8 people, 9 people. All right, who's brave enough to tell me why?
It's doing two things in one line of code.
Exactly. That line of code is doing too much. If I ask you what line of code 14 does, you have to give me 2 pieces of information. Oh, it creates a new node and then immediately sets its next, some other node, the next to that new node. There's nothing wrong there, but I like to be able to point to a line of code and say, oh, that line of code updates what the current node reference variable references. It moves it down one. If you're thinking, I want to be very clear, listen carefully. If you're thinking, well, he's doing that because he's teaching us and he's keeping it simple. No, this isn't for your benefit. It's for your benefit indirectly, but it's good design. Don't play code golf. Code golf is the idea of, I can do this in less code, with less code. Don't do that, that's bad. Yeah.
It's also like, no matter what happens, when you actually try to compile it, it's going to be the same speed anyways.
So at the end of the day, he's absolutely right. If you're like, yeah, but that's an extra set of instructions, that the computer needs to. No, the compiler, the program that takes your code and turns it into something that gets run on your computer, isn't going to give a shit about what your code actually says. It's going to optimize the hell out of your code beyond anything you're going to do anyways. So the actual difference, if you're like, yeah, but this is more efficient. No, it's not. Sometimes people will be like, oh, you've got 2. So you ever think to yourself, imagine I've got a function call, and this function returns some value that I need for an if statement. And I have 2 if statements. The if statement makes a function call with some parameter x, makes a decision, whatever, and a couple lines later, it makes the exact same function call with the exact same parameter, meaning that the result should be identical as before. And you look at that code and you think, oh, well, that's inefficient because I'm making 2 method calls, when really I could get away with 1 method call and store the result. Right? So just do it once and remember the result. so I can make my code better. Well, there's an argument to be made that it makes your code better. Absolutely. It can make your code better. Understandable, readable, easy to follow. But what actually gets run on your computer, I'm willing to bet I would put money on the compiler doing that for you, being like, oh, don't waste your time. Just do it once, save it. It'll do that for you. You're not writing the code for the computer. You're writing it for other humans, other people that are programming. The compiler writes the code for the computer. Very good observation. Yeah. Other questions? See, it's that type of nuance and stuff that I love to see students kind of pick up on and think about. Yeah.
Is head just a convention, or could you use any word or?
You could call it. Oh, here, by the way, here's like a neat feature of IntelliJ. You ever have like a variable that you've used a bunch of times? Now, there are a billion neat features in IntelliJ. I'm not going to touch on like any of them. But here's a handy one. Right-click, refactor, rename. There. Now, if I run it, it'll work just fine. There, yeah. Now, it did. The point I'm making is it did not need to be called head. Conventionally, you call it head, right? Unless you're using a specific context like a stack, then we would call it top, for example. But we'll see that momentarily. Any other last questions before we move on to the next topic? Keep it. Yes.
So, like in other programming languages, will the compiler like run the same way as like if because you said that it would just do it for you, like make it faster for you. But will other compilers do that, or do you have to take that into account with other languages?
It depends on the programming language, but I'm not an expert on all programming languages, but I'm going to make a very informed, educated guess that all actually well-used programming languages, compilers, yes, absolutely do that, right? Compilers are crazy. Yeah.
Most things compile down to C anyways, and like GCC does that, so.
So, yeah, if you're using a language that gets compiled to to your actual hardware, it's actually kind of interesting. So what you can actually do, like if you're in like a C or C++, for example, and you compile your code. So the code ultimately turns into the machine language. But you can actually compile it to like your processor's assembly language. And you can actually see, there's like usually settings for compilers where you say, how much do I want you to actually optimize my code? So you can actually compile it and then tell it to compile but don't optimize at all. And you can actually see how it changes the actual underlying instructions that get run on your computer. It's pretty cool. It's pretty cool. It's cool, at this stage it's cool as an exercise to just see the difference. Beyond that, I wouldn't worry too much about it. Yeah. All right. Good stuff. Keep up the good work, of course. All right. We built a stack with an array. But we saw with the array, we might run out of room, right? That was a pain in the ass. Expand capacity. Sure, we wrote that expand capacity method. It wasn't difficult or anything. We had to do it because arrays run out of room. But link structures don't. So maybe we could use a link structure to build a stack. So we built an array stack. Let's build a link stack. So remember, with the stack, this is what we got to do. In order to build a stack, in order to write a stack, to implement a stack, we need to implement the stack interface. We must. Sorry, we don't have to, but if we want to do it the right way, we must. But the value we get from actually implementing the interface is we now guarantee all programmers that this is a stack as defined by that interface. So anything you can do, anything that implements a stack will fit in the place where you need a stack. In order to do that, we need to implement push, pop, peek, is empty, and size. We'll also like maybe our equals and our toString as well. For the stack, that's what we need. So the stack interface also doesn't define how, but it says what it has to do. So let's implement a stack. Well, here's the general idea. We'll have a reference variable called top that will serve as, like you just kind of brought up, the head of the link structure. But we're not going to call it head, we're going to call it top here. And top is always going to reference the current top of the stack. We'll also have another field in our class called size that just keeps track of the size. Unlike the array implementation, where size kind of did double duty, right? Size we call top, and it happened to be the number of elements in the stack and the current next available spot. That's not a thing anymore because this is not an array. Top is referenced by some reference variable, but the field size is just the count, how many things are actually in there. So this is the idea. Top will reference the top of the stack. Size is the number of elements in the stack. If I wanted to push something onto the stack, so a moment ago we were just talking about the link structures, right? Inserting to the front, removing from the front. Inserting in the middle, removing from the middle. And the ends were the same. What operation would be pushing with respect to the link structures? Obviously we're adding. Where's it getting added?
To the end.
To the end? Who agrees? Uh-oh. You want to try again?
The front.
Who agrees? Yeah, there we go. See, you got it. We add to the front. Top is the beginning. So if we want to push something, we need to update top. So it's the whole process of just inserting to the front of a link structure. The new thing, you reference what top references, and then top references the new thing. That's how it's going to happen. And then pop. Pop, obviously we're removing something. Where are we removing from? It's not a trick question. The front. Once again, you remove from the front. The good news is adding and removing from a link structure, those are the easiest possible modifications. The front. So easy. So this is great. Push, we add to the front. Pop, remove from the front. Pop again, remove from the front. So let's talk about the implementation. Well, here's the start. Public class, link stack, T, it's generic. Implements stack. So we're implementing a stack again. And because we are telling Java that we're implementing a stack, that means we must implement the stack methods. And for the fun of it, let's see what happens if I go oh, it already exists? Oh yeah, it does. Great. There. I copy and pasted the code, but look, IntelliJ is mad at me. It's mad at me because I said this right here, this class, is going to implement a stack. But it's saying, well, hold on, you never implemented push. It'll also complain about not implementing pop and peek and size is empty. So it's mad about that. I can't compile this because it's like, no, you said that this class is implementing a stack. And you're not implementing a stack. You haven't implemented all the methods. So you are therefore not a stack. Thus, I cannot compile. The solution, of course, is, well, you just implement the methods. And the quick way around it is to just tell IntelliJ to make them. Now, they are clearly not complete or correct, right? Pop shouldn't just return null. But the point is that they exist, so at least it shuts IntelliJ up. So we're implementing a stack now, okay. How is it starting? Well, we don't need two constructors here. We don't really need it, right? Because you remember with the array one, we had two constructors. One was like the default one, where you created an array of some default capacity. Here, default capacity isn't a thing. There's no array. There's nothing that needs a default capacity. So we didn't also need another constructor where you could specify some initial capacity. So again, capacity is not a thing. We're not bound by some capacity of the array. So I just have one constructor. Top equals null because it's empty. It starts as empty. And size is 0 because, well, it's empty. Any questions? Push. All right. Let's look at the code. Push. Well, we make a new node with the element we want to add. To push. Next is top. Remember, we're adding the front. Top, you reference push now, or to push. Increase size, return true because, well, push returns a Boolean. This is just adding to the front. Right? I've got top. It could be null. And if it is null, it's fine, it doesn't matter. Top could be referencing null, it could be referencing a node that's one element, or it could be referencing a node that has a billion other elements after it. It doesn't matter. But what's happening is, I make the new node to, I don't know, I'll call it like TP. That's a T somehow. To push, right? It's a new node. I say to push, you're next. So your next is that. And then top, you don't reference what you were referencing, you reference the brand new node we just made. So now when I ask what top is, well, it's this node. We just add it to the front. Yeah? That's it. Update it, size there. Pop is going to be even easier. We'll check for is empty. I realize we haven't built is empty yet, but we will. If it's empty, well, we can't pop from an empty stack, just like an array, fine. Otherwise, you get the data from the element. Remember, we don't want to return the node. We want to return the data in the node. The node is just kind of like the container. So we want the element from the node. Top, in this case, top references this. I want to say, no, top, let's get rid of this now. Don't reference that anymore. Top, what's your next? Well, that's this one. Okay, yeah, you reference that now. What happens to this node? Who references it? Say nobody. Nothing, whatever. I like your answer. What happens to it? Goodbye. Yeah, it's gone. Nothing references it. It's gone. And if you think like, well, yeah, but it references this node is referenced by it. It doesn't matter if it's referenced by something. All that matters is I can't get to it anymore. We've lost reference to it. It fades into obscurity, and then the garbage collector comes along. Decrease size, return the element that we actually want. Peek is hilariously simple. Check if it's empty, fine. Otherwise, just return top's data. That's it. It's not supposed to modify anything. Size, and is empty. Size will return the size. Is empty is size 0. That's it. There, that's it. That is a linked stack. Now, we'll come back here on Tuesday, but here's some code I called playing linked stack. And look at line 5. Stack, my stack equals a new linked stack. If you go back and look at the code that I give you at the end of the array stack, called playing array stack, it is identical. It is absolutely identical with the exception of half of line 6. And the half is what type was actually made. Here, I made a linked stack on the right-hand side. Left-hand side is a reference variable for a stack. It doesn't give a shit what implementation it is. So the right-hand side here is a linked stack. If you go back to the array stack, well, in order to use the array stack, you just made an array stack instead. But the point is, they're both stacks. Because we can guarantee it, because they both implement stack. And if they all implement stack, we can call push, pop, peek is empty size, toString equals, and whatnot. All right, have a great weekend.